Welcome to day 43, Introduction to Machine Learning. In this session, we will cover the basics of machine learning and a dive into the popular libraries that make it easier to build powerful models. First, let's define what machine learning is. Machine learning is a subset of artificial intelligence that enables systems to learn patterns from data and make decisions or predictions without explicit programming. Some real-world applications of machine learning include image recognition, recommendation systems, fraud detection, and autonomous vehicles. There are three main types of machine learning. Supervised learning, where the data comes with labels such as predicting house prices. Unsupervised learning, where the data is unlabeled and the goal is to find hidden patterns like customer segmentation. Reinforcement learning, where systems learn through a trial and error approach, receiving rewards or penalties for their actions, like in game playing algorithms. Machine learning relies on a few key components. Dataset, a collection of data used for training the model. Features and labels. Features are the input variables and labels are the output variables we are trying to predict. Training and testing data. We split the data into training and testing sets to evaluate the model's performance. Evaluation metrics. These are used to access the model's accuracy, precision, recall, and F1 score. Now let's take a look at one of the most popular machine learning libraries in Python, scikit-learn. It provides a simple interface to build machine learning models with ease. Some of these features include built-in datasets like iris and wine, tools for pre-processing data, and a range of algorithms for training and evaluating models. To install scikit-learn, you can use pip, the Python package manager. Simply type pip install scikit-learn in your terminal. Once installed, you can import the library and check the version using print scikit sklearn dot underscore underscore version underscore underscore to ensure everything is set up properly. Let's walk through a basic hands-on example. We will use the iris dataset, which contains data about different types of flowers. First, we load the dataset and split it into training and testing sets. Next, we train a random forest model, and finally we evaluate its accuracy by checking how well it performs on the test data. Visualization is an important part of understanding your data. For example, we can plot the iris dataset using matplotlib to see how the different features are distributed. This helps in understanding the relationships between the features and is often the first step in any machine learning task. For further learning, you can check out some great resources. A highly recommended book is Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. You can also visit the official scikit-learn documentation for detailed guides. Additionally, FreeCodeCamp offers an excellent YouTube playlist on machine learning. For today's homework, I want you to try out the following. Load and explore another dataset in scikit-learn, train a logistic regression model, and evaluate its accuracy. Research and write down 5 real-world use cases of supervised learning. Welcome to day 44 of our journey through machine learning. Today we will focus on data pre-processing, a crucial step for preparing data before feeding it into machine learning models. We will dive into cleaning, transforming, and encoding data to improve model performance. Data pre-processing is vital because the quality of the data directly impacts the effectiveness of our machine learning models. Without clean, consistent data, even the best algorithms will struggle. Pre-processing helps us address missing values, reduce noise, and ensure that our data is structured properly, ultimately providing model accuracy and reliability. Data pre-processing typically follows a series of key steps: handling missing values, detecting and managing outliers, converting data types, and addressing imbalanced datasets. Each of these steps helps ensure that the data we use is suitable for training effective machine learning models. Cleaning the data involves handling missing or inconsistent values. For example, if there are missing values in our dataset, we can either remove those rows or fill the gaps with appropriate values such as the mean, median, or mode. This step ensures that our data is complete and ready for model training. Feature scaling and normalization are techniques used to bring the data into a standardized range. For instance, scaling ensures that numerical features are on the same scale, making it easier for algorithms like gradient descent to converge more quickly. Normalization brings all data values within a range like 0 to 1, ensuring that feature, no one feature dominates due to its scale. Many machine learning models require numerical inputs. Hence, we need to encode categorical data such as male or female into numeric values. Common methods include label encoding and one-hot encoding, which convert categories into numerical values while maintaining the integrity of the data. Outliers are data points that deviate significantly from the rest of the data set. We can identify these outliers visually using box plots or scatter plots, or statistically using methods like the z-score or interquartile range. Once detected, we can either remove or adjust these outliers to prevent them from distorting the results. Now it's time to put what we have learned into practice. For this task, we will work with the Titanic dataset. The goal is to clean the data by handling missing values, encoding categorical variables like sex and embark, and scaling numerical features like age and fair. By the end of this task, you will have a dataset ready for building machine learning models. When preprocessed data, always start by analyzing it to understand its structure and identify potential issues. Use pipelines to streamline the preprocessing process, ensuring that steps are applied consistently. And always document your changes so your work is reproducible and transparent. To summarize, data preprocessing is the foundation of building effective machine learning models. It ensures that our data is clean, scaled, and ready for analysis. For your homework, choose a dataset from Kaggle or the UCI machine learning repository, process it, and document your steps. This will help reinforce the techniques we have covered today. Welcome to day 45, Supervised Learning. In today's session, we will dive into the concept of linear regression and logistic regression, two fundamental techniques in machine learning. We will also explore their real-world applications and walk through hands-on examples. Supervised learning is a type of machine learning where we train models on labeled data. This means that the input data comes with known output labels. The goal is for the model to learn from this data so it can predict outcomes on unseen data. A few common examples include predicting house prices or detecting spam emails. In supervised learning, we use the input features to predict an outcome. Linear regression is a technique used for predicting a continuous numerical outcome. For example, we could use it to predict house prices based on features like square footage, number of rooms, and location. This method assumes a linear relationship between the input features and the output. In other words, as the features change, the output changes at a constant rate. In linear regression, we define a model as a linear equation. The model predicts the output based on the input features. The cost function, known as the mean squared error, measures how far off the predictions are from the actual values. We use a method called gradient descent to minimize this error and find the best fitting line. Now let's look at a hands-on example. Suppose we are predicting house prices based on various features. We will start by pre-processing the data, training the linear regression model, and then visualizing the results. With tools like scikit-learn in Python, we can easily implement this and generate a plot showing how well our model fits the data. Now let's move on to logistic regression. Unlike linear regression, which is used for predicting continuous values, logistic regression is used for classification problems. It predicts the probability of an outcome belonging to a certain class, like predicting whether an email is spam or not. The key function used here is the sigmoid function, which converts the model's output into a probability between 0 and 1. Logistic regression works by calculating the log odds of a certain event and transforming it into a probability. The logistic function or sigmoid function output values between 0 and 1. The model's cost function is cross entropy loss, which measures how well the predicted probabilities match the actual class labels. In a practical example, let's say we are predicting whether a student passes or fails an exam based on study hours. By pre-processing the data and training a logistic regression model, we can classify the outcomes as either pass or fail. Evaluating the model's performance involves looking at accuracy, precision, recall, and other metrics to understand how well it is predicting these outcomes. When building models, we need to be cautious of overfitting and underfitting. Overfitting occurs when the model fits the training data too well, capturing noise and leading to poor generalization. Underfitting happens when the model is too simple to capture the underlying patterns. Regularization techniques like L1 and L2 regularization can help prevent overfitting by adding a penalty to large coefficients. Once we have built our model, we need to evaluate it. A common practice is to split the data into training and test sets to assess how well the model generalizes. We can also use k-fold cross-validation to validate the model's performance by splitting the data into multiple subsets and training the model on different combinations. This ensures that the model performs well across different subsets of the data. In machine learning, the performance of a model can often be improved by tuning hyperparameters. Hyperparameters are the settings that control the learning process, like the learning rate or regularization strength. Methods like grid search and random search allow us to systematically explore different hyperparameter combinations to find the best configuration for our model. Let's put everything together in an end-to-end project. We will load and clean the data, train a model using either linear or logistic regression, and evaluate the results. For example, in a project predicting heart disease, the model could classify patients as either at risk or not based on features like age, blood pressure, and cholesterol levels. To recap, we have learned that supervised learning involves training models on labeled data to predict outcomes. We have covered both linear regression for numerical predictions and logistic regressions for classification tasks. It's essential to practice these concepts through hands-on examples to fully understand how they work and how to apply them effectively. For homework, I recommend implementing linear and logistic regression on new datasets. You can experiment with regularization techniques like the ridge and lasso. I also encourage you to explore Kaggle competitions where you can apply these techniques to real-world problems and further sharpen your skills. Thank you for your time today. I hope you enjoyed this session on supervised learning. Don't hesitate to revisit any of the examples we covered and experiment with them on your own. Welcome to day 46 of our machine learning course. Today we will be diving into the world of unsupervised learning, focusing on clustering techniques and decision trees. By the end of this session, you will have a good understanding of how unsupervised learning can uncover hidden patterns in data. Here's an overview of today's topics. We will begin with an introduction to unsupervised learning and then explore some powerful clustering techniques like k-means, hierarchical, and db-scan. After that, we will take a look at decision trees and their applications in data classification. Finally, we will wrap up with some hands-on practice to solidify your understanding. Unsupervised learning is a type of machine learning where we work with data that does not have labels or predefined outcomes. Unlike supervised learning, where we train the model with labeled data, unsupervised learning allows us to find hidden patterns or groupings in the data. It's ideal for tasks like clustering, dimensionality reduction, and finding with associations between data points. There are three main types of unsupervised learning. First, we have clustering, which involves grouping similar data points together. Second, association helps us discover relationships between variables. Finally, dimensionality reduction simplifies data by reducing the number of features, making it easier to analyze while retaining essential information. Let's start with clustering. Clustering groups data points into clusters based on their similarities. It's widely used in customer segmentation, anomaly detection, and even image segmentation. The goal is to identify natural groupings within the data without needing any predefined labels. One of the most popular clustering algorithms is k-means. The idea behind k-means is simple. We choose a number k for the clusters, randomly assign centroids, and then assign data points to the nearest centroid. We repeat this process, recalculating the centroids until they stabilize. It's a straightforward yet powerful technique for many real-world clustering tasks. Here's an example of how k-means work. We start by selecting k initial centroids, then each data point is assigned to the nearest centroid. Over time, the centroids are updated and the data points are reassigned based on the new centroids. We can determine the optimal k by using the elbow method, which helps identify the best number of clusters for your data. Next, let's talk about hierarchical clustering. Unlike k-means, which divides data into a fixed number of clusters, hierarchical clustering builds a tree-like structure called a dendrogram. diagram, this tree shows how clusters are nested within each other, which can be useful for understanding relationships between data points at multiple levels of granularity. Another important clustering method is DBSCAN, density-based spatial clustering of applications with noise. DBSCAN is great for handling datasets with noise and irregular shapes. Instead of specifying the number of clusters, DBSCAN groups points based on density, making it ideal for complex, non-linearly separable data. Now let's shift gears and look at decision trees. Decision trees are a supervised learning technique, but they are incredibly useful in understanding how data can be split and classified. They work by recursively splitting the data based on feature values, with each split maximizing the separation of the classes. This process creates a tree structure with decisions at each node, which makes it easy to visualize and interpret. A decision tree works by splitting the data into subsets based on feature values that best separate the classes. To decide how to split the data, we use metrics like Gini index or entropy, which help determine the quality of the splits. The tree grows until all the data points are classified, and we can prune it to avoid overfitting. Let's now put this into practice. We will use a dataset such as the Titanic survival dataset to build a decision tree. Using a tool like scikit-learn, we will create a tree that classifies whether a passenger survived or not based on features like age, sex, and class. We can visualize the tree to see how the decisions are made at each step. To reinforce what we have learned, here's your practice assignment. Use a movie ratings dataset to perform clustering and group similar users based on their performances. Once you have created the clusters, analyze the results and try to interpret the patterns in the data. This hands-on experience will help solidify your understanding of supervised learning. To summarize today's lesson, we learned that unsupervised learning helps us discover hidden patterns in data. We explored several clustering techniques like k-means, DB-scan, and hierarchical clustering. We also introduced decision trees and their application in classification tasks. Remember, practice is key, so continue experimenting with these techniques to master them. That wraps up today's lesson. If you have any questions, feel free to ask now. I hope you found this session informative and helpful in your journey to understanding unsupervised learning. Thank you for joining, and I will look forward to seeing you in the next session. Welcome to today's lesson on Natural Language Processing or NLP. In this session, we will explore the fundamentals, techniques, and applications of NLP. Let's dive into how machines understand and process human language. NLP is a subfield of artificial intelligence focused on enabling machines to interpret, understand, and generate human language. It's all around us, from chatbots to voice assistants, and even in sentiment analysis for social media. NLP is a key technology driving intelligent systems in today's world. The NLP process follows a series of text steps, starting with data collection, where we gather the text data. Next, we pre-process the data. This includes cleaning and preparing it for analysis. We then extract features, train models, and evaluate them for accuracy. This pipeline is essential for successfully processing and interpreting text in various real-world applications. Let's break down some key text processing steps. First, we have tokenization, where we split text into smaller units like words and or sentences. Then we removed stop words, the common word like is or the that don't carry much meaning. Stemming and lemmatization are the next steps where we reduce words to their base or root form. For example, running becomes run. This helps simplify the language for processing. There are several ways to represent text data numerically for machine learning models. Bag of words (BOW) is a simple approach where we count the efficiency of each word in the document. Another technique is TF-IDF, which gives more weight to words that are important to specific documents but rare across all documents. Finally, word embeddings like word2vec and glowvec represent words in dense vectors and capture semantic meaning based on context. One common application of NLP is sentiment analysis, where we classify text as positive, negative, or neutral. For example, we can analyze movie reviews to determine if they are favorable or not. Using libraries like NLTK for pre-processing and scikit-learn for building the model, we can classify sentiment effectively. This helps businesses gauge public opinion on their products or services. Named entity recognition or NER helps us identify and classify named entities in text such as names, locations, and dates. For instance, in the sentence Barack Obama was born in Hawaii, NER will recognize Barack Obama as a person and Hawaii as a location. Tools like SPA-CY make this process fast and accurate. Let's now look at some best practices. When working with large datasets like libraries like SPA-CY are optimized for speed. Handling language ambiguity such as sarcasm or polysemy is one of the biggest challenges in NLP. Additionally, dealing with multilingual data or non-standard text like slang requires robust models and data processing techniques. Despite the advancements, there are several challenges in NLP. Poor quality or noisy data can lead to inaccurate results. Contextual understanding is another hurdle, especially when dealing with ambiguous meanings in language. Lastly, multilingual NLP requires special techniques to work effectively across languages, making it a complex task. If you are looking to dive deeper into NLP, some excellent resources include libraries like NLTK and SPA-CY, Spacey. You can also practice on publicly available datasets such as the IMDb movie reviews or Twitter sentiment analysis dataset. Platforms like Kaggle offer real-world NLP challenges, and Google Colab provides an easy way to run your models in the cloud. To summarize, natural language processing helps machines understand and interpret human language. We covered techniques like tokenization, stop word removal, stemming, lemmatization, TF-IDF, and word embeddings. These tools are used in various applications including sentiment analysis and named entity recognition. Next steps: start experimenting with NLTK and Spacey to build your own NLP models. That wraps up today's lesson on NLP. If you have any questions or would like further clarification on any of the topics, feel free to ask now. I would be happy to help. Welcome to day 48 of our journey into deep learning. In today's session, we will dive into the basics of neural networks and explore how to use TensorFlow and Keras for building deep learning models. Deep learning is a subset of machine learning that utilizes neural networks with multiple layers. It allows computers to learn from large amounts of data, enabling them to perform complex tasks like image recognition, space recognition, and even self-driving cars. Deep learning powers many of the advanced AI systems we use today. A neural network consists of several key components. The input layer is where data enters the model. The hidden layers are responsible for processing the input, extracting features, and learning from the data. Finally, the output layer produces the prediction or classification. We also use activation functions such as ReLU, sigmoid, or softmax to introduce non-linearity, allowing the network to learn more complex patterns. Forward propagation is a process where input data is passed through the network to make predictions. Each neuron in the network performs a weighted sum of the inputs, adds a bias, and passes the result through an activation function to produce an output. This is how the model makes predictions based on the data it has seen. Backward propagation or backpropagation is a process of adjusting the weights and biases in the network based on the error or loss. It works by calculating the gradient of the loss function with respect to each weight and then using optimization algorithms like gradient descent to update the weights. The goal is to minimize the error and improve the model's accuracy. TensorFlow is a powerful open source library developed by Google that facilitates building and training deep learning models. Keras is a high-level API that sits on top of TensorFlow, providing an easy-to-use interface for constructing complex neural networks. Today, TensorFlow and Keras make deep learning accessible and efficient. To get started with deep learning, we need to install TensorFlow and Keras. Simply open your terminal and type pip install TensorFlow. We recommend using Python 3.x and a Jupyter Notebook environment for an optimal development experience. Once set up, we are ready to build our models. Let's dive into building our first simple neural network. We will use the MNIST dataset, which contains images of handwritten digits. Before training the model, we pre-process the data by normalizing the images and reshaping them to fit the model's input requirements. Our network will have one or more hidden layers and an output layer with 10 nodes, corresponding to the 10-digit classes. Here's a basic example of how to build a neural network using TensorFlow and Keras. First, we import the necessary modules. Then we load the MNIST dataset and normalize the data. Next, we define the model architecture using Keras sequential API, adding layers like flatten, dense, and the output layer with a softmax activation function. Finally, we compile the model, specifying the optimizer, loss function, and evaluation metrics, and train it with the training data. Once our model is defined, we train it using the training dataset with model.fit. This process adjusts the model's parameters to reduce error. After training, we evaluate the model on the test dataset using model.evaluate. The evaluation gives us an understanding of how well the model generalizes to new unseen data with metrics like accuracy and loss. Overfitting occurs when the model performs well on the training data but poorly on new unseen data. To address this, we can use techniques like dropout layers or regularization. Underfitting happens when the model is too simple and not doesn't capture the underlying patterns in the data. In this case, we can increase the model's complexity or provide more data to help it learn better. Now let's put our knowledge to practice. We will build and evaluate a neural network on the MNIST dataset. As we train the model, we visualize the accuracy and the loss curves to monitor the model's progress and performance. Today, we learned the fundamentals of deep learning and neural networks. We explored the structure of a neural network, the processes of forward and backward propagation, and how to use TensorFlow and Keras to build models. We also touched on strategies for handling common performance issues like overfitting and underfitting. Thank you for your attention. I would now like to open the floor for any questions or clarifications you may have. Welcome to this mini project on building a basic machine learning model. In today's session, we will walk through the steps of applying machine learning concepts to a real-world problem. Specifically, we will build a spam email classification model covering data pre-processing, model training, evaluation, and deployment. The primary objective of today's mini project is to create a simple machine learning model. We will apply the concepts we have learned over the past few weeks, focusing on real-world applications like spam email classification. By the end of the project, you will understand the full pipeline of machine learning from data pre-processing to model deployment. Let's start by defining the problem. For this mini project, we will be working on a spam email classification task. Our dataset will include features such as email content, sender, and subject, and the goal is to classify each email as either spam or not spam. By building this model, we will learn how to handle and process real-world data efficiency. Before we dive into training the model, we need to pre-process the data. This includes handling any missing values by fitting or removing them. Feature scaling is crucial to ensure that all the features are on the same scale, and we will also need to encode any categorical variables to numeric values. This is where we will use tools like Python's pandas and scikit-learn to clean and prepare the data for modeling. Once the data is pre-processed, we can move on to selecting and training a model. For this mini project, we will use supervised learning, specifically algorithms like logistic regression or decision trees. We will split the data into training and testing sets and then train our model using scikit-learn. To optimize performance, we will also experiment with hyperparameter tuning. After training the model, we will need to evaluate its performance. We will look at several key metrics such as accuracy, precision, recall, F1 score, and ROC AUC. These matrices will help us understand how well our model performs, especially on imbalanced classes like spam versus not spam. We will also generate a confusion matrix to see where the model is making errors. To improve the model, we will compare different algorithms and see which one performs better. We might also tune the model's hyperparameters or try additional feature engineering. Documenting the results and identifying areas for improvement is an essential step in ensuring that the model performs at its best. Once we have trained and evaluated model, we need to deploy it. We will save the trained model using Python's joblib or pickle, which will allow us to reuse it in the future. Optionally, we can create a simple app using Flask or Streamlit to make real-time predictions on new data. Documentation is an important part of the project. It should include details about the dataset, pre-processing steps, model selection, and the performance evaluation. It's also crucial to document how to use the model for predictions. In summary, we have covered the entire machine learning pipeline, from data pre-processing and model training to evaluation and deployment. That wraps up the mini project on building a basic machine learning model. Do you have any questions or comments? Feel free to ask, and I would be happy to clarify anything you might be uncertain about.